All right, let's compare these two populations with each other. We have population 1 and population 2. Now, in each of these cases, we have very small populations, only 6 data values in each one. But we're trying to make this a manageable workload for us. Now, to calculate the mean for each population, simply add up your number of data values and divide by how many you have, 6 in each case. And if you were to do that, you'd find that they both have the same population mean of 7.5. So they have the same measure of the middle. But what about their spread? And by spread, I mean how spread out the data values are. Let's look at a little picture of that. So each of these data values for population 1 are plotted on the number line. So you can visually see how spread out they are. Doing the same thing for population 2. Notice we've got repeats, so those pile up here. You can see there's very little spread in population 2. They're close together. Whereas for population, they're more spread out. So visually, we can see that there's a difference in spread. But in statistics, we want an accurate way to measure that. So let's consider this. Let's look at all the distances between each of these data values and the mean. That's what these brackets are showing us, all these distances between each data value and the mean. Same thing for population 2 here. So this is what we're doing here in these columns. Under X, which represents data value, is a list of all our data values. Then over this column heading, this just tells us what we're going to do in this column. We're going to take each data value and subtract the mean from it. What does that tell us? It tells us the distance between that data value and the mean. That's what all these brackets are representing. So let's do that. Now, if we take the data value 2 and subtract the mean from it, 7.5, what do we get? Well, I bet you could do that in your head. But if you have any doubts, on your calculator, 2 minus 7.5 gives us negative 5.5. And so let's go ahead and put that in. Now, so let's continue on down here and do that for each of our data values. Now, what is 3 minus 7.5? A negative 4.5. And our next one, what is 7 minus 7.5? A negative 0.5. Oh, here, let me make that red so it looks like all my other answers. And what is 8 minus 7.5? Well, notice that is a positive 0.5. Now, let's make a note here. Why is this one positive while these were negative? Well, you'll notice that all data values that are to the left of the mean will have negative distances. And all the data values to the right of the mean are going to have positive distances. And so if we do a 12 minus 7.5, we're going to get a positive 4.5. And for our last one here, 13 minus 7.5 is a positive 5.5. Now, if we were to add these distances all up, what would it add up to? Well, we could do that on our calculator here, but you might be able to just look at this. Positive 5.5, negative 5.5. Positive 4.5, negative 4.5. Hey, this is going to add up to 0. Does that always happen? Yes, it does. It always adds up to 0. Because that's the very definition of what the mean tells us. It's the middle such that all the distances to the left equal all the distances to the right. So this will always add up to 0. You say, well, that's a heck of a note because you see, I wanted to add up all those distances, divide by how many I have to get an idea of the average distance between the data values and the mean. Well, that's why we're going to go over here to this column and we're going to square each of these distances. So whatever values here, we just square it and put it here. That's what this notation, that column heading, is telling us to do. First, you find the distance between the data value and the mean, and then you square it. Now, hopefully you're well aware that squaring a negative number is always positive. So over here on the calculator, I put in a negative 5.5, and I square it. It is a positive 30.25. So let's put that in. Now, we've mentioned this earlier when working on the TI-83, but in case you forgot, what would happen if I did it this way? Negative 5.5 and hit the x squared. In other words, just like I did before, but without the parentheses. What? Why did it give me a negative 30.25? Well, order of operations. First, it did the exponent, it squared it, and then it did the negative. So first we squared 5.5, got 30.25, and essentially multiplies it by negative 1, giving me that answer. But you know it's positive, and the idea is you would need to use parentheses there. Now, so let's go ahead and let's square our negative 4.5, and we get 20.25. Put that in, and then we go over here, and we want to square our negative 0.5. You can do that on your calculator on your own. You'll get a positive 0.25. Oh, let me make that red. There we go. And same thing here. You square that, it'll be a positive 0.25. And then you square a positive 4.5, and you're going to get a positive 20.25. And you square a positive 5.5, and you're going to get a positive 30.25. Now this over here, now notice this notation. That summation symbol simply says add up all of these. And what are these? Well, that's the column heading. So you're going to add up all those distances between the data values and the mean, and always add it up to 0. Over here it's saying add up all of these. And what are these? Well, that's the column heading. You're adding up all the square distances between the data values and the mean. So you add up that column. And we do that on our calculator here. Just add them right up. And we come up with 101.5. So let's put that answer in there. 101.5. Oh, I'll go 2 decimal places because that's what my previous work was in. And let's get this to line up a little more nicely. All right, so on your own, why don't you go ahead and fill in for population 2, doing the same thing that we just did over here. So hit the pause key on your video playing, and then once you're done, hit the play button and see how you did. All right, you're back. Okay, so let me go ahead and I'll get this all filled in here. There we go, and I'm going to shift this over. There we go. So notice that when you added up this column here, you got 0. If you didn't, you did something wrong. And then when you squared each of these, notice they're all positive. You added them up, you got 5.5. So notice that the sum of all the squared distances between the data values and the mean is 5.5, which is much smaller than the sum of all the squared distances over here. Now, in your homework, when you do this, there is only one reason why we're having you do the hand calculation is that so you will think about what you're doing. In other words, imagine this, if you will. You've got an imaginary friend, perhaps an annoying little friend who always says, "What are you doing that for? Why'd you do that? Huh? Why?" Well, you'd be able to explain to them, well, what I'm doing here is I'm finding the distance between each data value and the mean, and that's what I'm doing here. And then the annoying friend says, well, why are you squaring it for? Why? That's a lot of work. Why would you do that? Well, the reason is this always adds up to 0. And I don't want it always adding up to 0 because I'm not getting anywhere. I've got to try and find an average of these distances. So I'm squaring it because then I always get positive values and that will add up to something besides 0. Now, of course, you're going to say, well, what are you going to do with this? Well, that's what we're getting to next. There's a thing called the variance. And all that is it takes the sum of all these squared distances and divides it by how many data values you have, which is 6. So basically, it's the average of the squared distances between the data values and the mean. And it will measure a spread for us. For example, if I take this 101.5 and I divide it by n, remember n is the number of data values of my population, 6, so my variance is 16.92 if I round off. Whereas for population 1 here, I'd be taking the sum of my square distances, 5.5, and divide it by my number of data values, 6. Its variance is only 0.92. Quite a bit smaller than over here. And now, see, we have a way of measuring that. So let me go ahead and put in my work here. Now, I went out 4 decimal places here. You might be wondering why I just didn't round off to 2. Well, you see, I'm going to use this as an intermediate calculation for what I'm going to do next. Because this is the problem with variance. Whatever you're measuring in, whether it's inches or miles or pounds or degrees Fahrenheit, whatever it is you're measuring, will be in these such units here. But variance will always be squared units. Inches squared, feet squared, seconds squared. Well, wouldn't it be nice to have a measure of spread that's in the same units as what you were actually measuring in? Sure it would! And that's what we're going to do next here. All we're going to do is take the square root of the variance, and that'll give us what we call the standard deviation. So notice the symbol sigma. It's the Greek letter for S. S as in standard deviation. And sigma squared is your variance. So if I just take the square root of my variance, I'll get what I really wanted all along, the standard deviation. So on my calculator, I press the yellow second key, then the x squared key gets me the square root symbol, and I can put in my 16.9167, right parenthesis, and I see my standard deviation is 4.11 for population 1. Let's do this for population 2. Its variance was 0.9167, right parenthesis, and its standard deviation is only 0.96. So let's go ahead and put that in here. All right. Now, you might be wondering, now what is the standard deviation telling us again? Well, one, it is a measure of spread, but you notice how the square root sort of kind of undoes the squaring we were doing up here earlier? So think of the standard deviation as the standard or typical deviation or distance between the data values and the mean. So if you want an idea of what the average distance is between the data values and the mean, that's what the standard deviation tells you. And when you do it for different populations, you can tell which one has the most spread. So which one has the most spread? Population 1. The bigger the standard deviation, the bigger the spread. The smaller the standard deviation, the smaller the spread. And so, that's what we based our decision on. It had a larger standard deviation. Now, let's get back to that annoying imaginary friend I was telling you about. The last thing you want to do in your homework when you're doing this is to just go through it mindlessly, just going through the steps and not knowing why you're doing it. You're wasting your time. So, think about what you're doing. So what does x minus mu tell you? Why are you doing this over here? Just for the fun of it? I don't think so. So that tells you the distance between a data value and the mean. Notice it's negative when x is less than the mean, and it's positive when x is greater than the mean. And the sum of them always adds up to 0. So that's a nice little thing to tell that imaginary annoying friend of yours. Now, the column after that, why are we squaring this x minus mu? Why would we do that? Well, the squared distance between a data value and the mean. That's what it represents, and it's always positive. So it's going to add up to something besides 0. Now, what does this tell you? Well, I suppose you could say the variance, but I think it'd be a little more informative if you stated what the variance is telling you, which is the average of the squared distances between the data values and the mean. And the last question, well, if we take the square root of that, what does that tell you? Well, I guess you could say the population standard deviation, but I think this would be quite a bit more informative. It's the typical or standard distance or deviation between data values and the mean. It's basically the average distance between all the data values and the mean. So isn't the name standard deviation a swell name for it? It really tells you what it's doing.